Hey, Zach.
Hey, Phil.
How you doing?
All right.
This is Zach. He's a mechanical engineer, and you build machines for a living, right?
That's right.
Great, because I need help building a catapult.
Okay, but what's with the pumpkin?
Well, the pumpkin is what I want to throw out of the catapult. See, I figure we just take the small design and we just make it so that we can throw one of these. What do you think?
You're gonna need a really big catapult.
Yeah, and I'm also gonna need some really big elastics. Where do you get those?
Well, in medieval times, they used rope to make large catapults.
Oh, okay, well, rope is a lot easier to get, and that would be fine. And I want to make this arm as long as this piece of wood here.
This is gonna be a huge catapult.
It's a huge catapult. I guess we should build it outside, though, huh?
Let's do it.
Okay, it's over that way.
Okay.
I'll follow you.
Sure, do you want a hand with that?
No, I'm fine. You go ahead, and
Okay.
I'll just, maybe if you hold the door open for me, I could just hold, no, you know what, you go and I'll meet you.
You sure you're good?
Our full-size catapult is going to look a lot like the popsicle stick version. We start with a 4-sided frame and add some legs on the bottom. Our spoon is going to be replaced by a long throwing arm with a basket on the end. Then we need a really strong cross brace at the top to stop the arm. Just like in the small version, using a triangle shape is the best because triangles are very strong. Finally, we need something to wind around and around, which is going to give us our elastic force. Instead of elastics, we're going to be using rope for our catapult because rope has just the right amount of elasticity. But unlike medieval times, we're going to be catapulting pumpkins. Once Zach and I got it all put together, it looked like this.
Okay, we have built a catapult. Check it out. It's pretty solid, and I think it's pretty amazing. And just like in the small catapult, we have our elastic force. But this time we're using rope, right, Zach?
Yes.
Okay, and rope will work as well as the elastic did in the small one?
Yeah.
All right, great. So what do we do? It's really loose now.
We need to wind this up so that we put some tension into it.
Go!
The reason a catapult works is because the rope is twisted. The elasticity in the rope wants to unwind, which gives the catapult its power. Just like the small catapult, the more you wind it, the better it works.
Good. Usually in medieval days, they had whole teams of people doing this job, but it's just me and Zach now. How you doing, Zach?
All right.
Okay. And then we clamp it on here. So the thing doesn't unwind, right?
Yeah.
Good. All right, now we have our pumpkin, and we're gonna fire our pumpkin in our castle wall, which is made out of cardboard boxes over there. Pumpkin. All right, here we go. Pulling the arm back. Oh, that elastic force is pretty strong. Okay. How do you think you think that pumpkin's a good size?
Oh, it's pretty big.
You think?
Oh, a little too big.
It's too big for our basket. Yeah. Smaller pumpkin! Smaller pumpkin! I'll hold this. No rush, Zach. No rush. Okay, rush, Zach. Can't hold.
Oh, yeah.
Can't hold arm. Okay, ready? 1, 2, 3! It didn't work that well.
No, not quite that well.
Yeah, so it went, and it flew, and it landed here, which is a little farther away from the wall than I'd like it to be. 1/3 of the way to the wall! I don't know if that's enough. What do we do to make it better?
Well, the way we're throwing it right now, we just have the pumpkin in a, at the end of the arm. But if we make some kind of a sling so that we fling it as we're bringing it up.
We make a sling?
Yes.
All right, I don't know how to make a sling, but you know how?
Sure.
All right, we'll make it, and then you can explain how it works.
Yeah.
All right, good. Let's put the pumpkin over here. We'll recycle it later.
Max Historica.
Good morrow to you. I am Lord Fillington III, and welcome to my medieval castle. Throughout history, lords and kings have built castles and walls to keep people out. I built my castle to protect my prize collection of snow globes. I have so very many, and they're all mine. Ha ha! Oh, hello! You down there! You can't come in. This is my castle.
And throughout history, there have been people who've been wanting to get into those castles because Lord Fillington has been hogging all the snow globes, and I'd like to look at them. But the hard part is figuring out how to get into the castle, because I can't just come up to the wall and start hammering on it. Huh?
Taste the wrath of my water balloon!
Because if I get too close to the castle, he can get me.
Ha 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 ha! Fortunately, there's this thing called a catapult.
Oh, fiddlesticks. They have a catapult.
What you do is you put something heavy in the end here, and the catapult fires it at the walls of the castle, knocks them down, all from far enough away that the people in the castle can't get to you. Ah! Oh, I surrender! Don't knock my walls down! It'll take me all week to fix them. Oh.
All right, you can have a snow globe.
And that's how catapults were used in history. Oh, so beautiful.
Back to our maxed out catapult. Our first design threw a pumpkin just like it was supposed to, except it only threw it 1/3 of the way to the wall. Now Zach and I are planning to outfit the catapult with a sling. The sling attaches to the end of the throwing arm and gives the pumpkin a lot more distance to travel. Because the pumpkin is traveling a longer distance in the same amount of time, it will be going faster, which will hopefully get it to the wall, or at least a lot farther than before.
So we built this sling. How does this work, Zach?
Well, we've got one end tied here.
Yeah.
And then we put the pumpkin in here.
Wait. Okay, pulling arm down. Pulling arm down. Okay, yeah, now what?
Now we put the pumpkin in here.
Put the pumpkin in there.
Yeah. And we loop this over the back of the, over that. As the throwing arm goes up, this will slide off the back of the throwing arm and it will release the pumpkin.
All right, you're the expert. I believe you. Let's try it out. 3, 2, 1. Whoa! Okay, that works really well. You know what the problem is, though? We still don't have enough oomph.
Yeah, it needs more power.
So what do we do? I don't know if we can crank that rope anymore.
I think we're at the limit of our rope power, but if we added some more elastic.
I thought we weren't going to use elastic.
Well, we used elastics in our small demo model, so what if we use some more?
We have elastics? I don't know
yeah,
if we
got
have...
some in here just in case.
What's this?
It's surgical tubing.
It's like a giant elastic. Well, I guess this is elastic force. So do we twist it around at the bottom there?
Well, we just wrap it around the throwing arm like this.
Oh, I see. So we tie it here.
Yeah, we just need a lot more, and then
we pull this, and it would be. Oh, yeah, that would make a lot more. So we just need a lot more of this elastic. What is this again?
Surgical tubing.
Surgical tubing. It's like a giant elastic. Fantastic. All right.
Goggles on.
Goggles on. Yes. Yes.
Here's another fun way you can play with elastic force. Take a milk carton. I prefer Science Max milk because it's the creamiest. 2% cream, 100% science. Wrap some elastic bands around it with some popsicle sticks on the bottom, sort of like feet. Then take some clamshell packaging, which wraps just about anything you buy nowadays, and cut out a square or a rectangle. Then wrap some tape around that square with an elastic in it, and put the elastic on the feet of your milk carton. Then wind it around and make sure you go backwards so your paddle wheel boat will go forwards when you put it in the water. And there you go, a paddle wheel boat. Now it is time to max it out. Ahoy, the SS maxed out elastic force paddle wheel boat mattress. I need a better name. But I've made a giant paddle wheel boat that will work on elastic force because I've got surgical tubing as my elastics, and that's an air mattress. And then I use some lumber to hold it all together. And of course I need a paddle wheel, and what better thing to use in a pool than a flutterboard? Okay, here we go. So normally you're not allowed to wear your clothes and your shoes in the pool, but I got special permission because of science. Besides, I'm not worried at all, so I didn't wear my swimming outfit because I figure I can totally do this entire experiment without even getting wet. That is how confident I am. All right, now the tricky part we'll be getting onto the mattress. Okay, here we go. Ha-ha! Whoa. Ha-ha! The SS Science! Hey, SS Science, that's a great name for this. Look, it works great, and I managed to stay totally dry. Huh? Well, almost. Whoa, whoa, whoa. Haha, you thought I was gonna fall in the pool, but I didn't. Uh-oh. My flutterboard has stopped moving, and I'm in the middle of the pool. Almost. Yeah. Didn't think this through. No. 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 No, that's not going to work. Maybe I'll wait. Our maxed out catapult was working well with the sling we attached to it, but it still didn't make it all the way to the wall. Zach's idea is to attach a bunch of surgical tubing to the cross piece of the catapult. Surgical tubing is pretty much big elastics, so we'll have two places we're getting elastic force from, the rope and the surgical tubing. Hopefully this design is enough to help our catapult fling a pumpkin far enough to hit the castle wall.
All right, here we go. You hold that. I get this. We got our system down now. Okay. This goes up to there. Okay. Okay. 3, 2, 1. Nope. One, 2, 3. Oh! Oh! It went too far. It went too far. That's so good. Oh man. Okay, so all we gotta do is move the catapult back. So you get that side, I'll get this side, and we'll move the catapult. See, now our catapult is too good. We gotta back it away from the castle. All right, let's go again. Aha, pumpkin.
Pumpkin.
Pulling arm back.
Pulling arm back. Grunting.
Floating pumpkin. Hooking rope on arm.
Hooking rope on arm. More grunting.
More grunting. Pulling back strongly. 1, 2, 3. Oh, 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 wow. Woo.
We're inside the castle.
We're still inside the castle. Oh man, it's an excellent shot though. So what do we do? Move the catapult back?
Yeah.
Move the catapult back! Today we're talking about states of matter. Now there are 3 main states of matter. Solid, like this table, liquid, like the water in this beaker, and gas. Yes, thank you. And we're also gonna be looking at the things that kind of go in between. Things that are sometimes solid, sometimes liquid, like cornstarch mud, which is very easy to make. All you need is water and cornstarch, which you can get at the grocery store. Mix it up however much you want. Just remember, 2 parts cornstarch to 1 part water. Twice as much of this than you have of that. Very easy. Mix it up and you get cornstarch mud, which sort of seems like a liquid unless you hit it. And then it becomes solid. But if I pour it, it's a liquid. Even if I hold it in my hand and I hit it really fast, it turns into a ball. And it will stay in a ball as long as I keep hitting it or squeezing it. But soon as I stop, it turns into a liquid again. Now, we're gonna max this out. We'll go through the portal and learn more about solids, liquids, and gases. Yeah, right. That's why I'm going to the Center for Skills Development and Training. And, oh no, wait, that's the code for the fog machine. Wait, stop. Stop. It seems to be stuck. Oh, never mind, never mind. I'll fix it later. Right. Hey, Judy, how are you?
Hi, Phil. How are you?
Good. Judy is going for her PhD in chemistry, right?
Yes.
Fantastic, because that means you can explain cornstarch mud to me. Now, is this a solid or is it a liquid?
Well, it kind of has properties of both. It's called a non-Newtonian fluid, so that makes it a liquid.
A liquid? Well, I mean, it pours like a liquid, but when you hit it, it's a solid. So why does it turn solid when you hit it?
So when you're pouring it, the particles are still far apart, so they can't interact with each other, and so they stay a liquid. But when you're hitting it, you're jamming the particles together, and they line up to become a solid.
Now, does it still work the same way if we have a lot more of it?
It should.
Great, because I've got this 20-kilogram bag of cornstarch, and I have 34 more of them.
Wow, that's a lot. But I think you'll need a much bigger container.
Much bigger container. Great. I got some wood over there. Why don't you go, and I'll follow you.
All right.
I'll follow you. I'm coming. Yeah, thanks, Ramona. And give me one of them fizzy drinks. Not too fizzy, just sort of medium fizzy. Thanks a lot. Hello, do you have trouble knowing what is a solid, liquid, or gas? Are you confused by Jell-O? I mean, which is it? Is it a solid or is it a liquid? Water is a liquid, but what about when it's ice? Well, you gotta know your states of matter. There are three main states of matter: solid, liquid, and gas. And there are three rules that you need to figure out which one of them is which. Does it flow? Does it fit the shape of its container? And can you squeeze it? Rule number one, does it flow? Solid, liquid, gas. Here's a gas. Does it flow? Do the particles pour over each other and cascade down? Yeah, they do. Does a liquid flow? Yeah, it does. Does a solid? Nope. Rule number two, what happens when you put it in a container? Does it take the shape of the container? Gases take the shape of the container. Liquids takes the shape of the container. Solids do not take the shape of their container. I know what you're thinking. You're thinking, I get the whole pouring and taking the shape of the container, but come on. Liquids and gases, they do both of those things. Well, it all comes down to rule number three. Can you squeeze it? Now, solids, you can't really squeeze them. Liquids, you can't really squeeze them. Gases, bam, you can squeeze them. You see, gases compress. Liquids and solids, they don't really compress very well. The other difference between gases and liquids is gases will take the shape and the volume of the container they're put in. Liquids don't do that. So there you go. Solid, liquid, gas. And the rules. Does it flow? Does it take the shape of the container? And can you squeeze it? Now you know your states of matter. That'll be $6.50. Cash only.
So what is cornstarch mud and how does it work? Well, cornstarch mud is a non-Newtonian fluid, which means it behaves differently than you, or Newton, would expect. Here's cornstarch, and here's water. Cornstarch is made up of large, blocky molecules like this. Water is made up of much smaller, rounder molecules like this. When you put them together, it looks something like this. It all has to do with how the molecules slide past each other. When you put light pressure or slow pressure on the mud, the water molecules and cornstarch molecules have time to shift out of the way. But when you put a sudden pressure on it, the water molecules squirt out of the way, but the cornstarch molecules don't have enough time. So you get a section that's nearly all cornstarch, which acts as a solid. Cornstarch mud is a shear thickening fluid. Shear is talking about the force of things sliding around, in this case, the molecules. So when the shear force is strong, the fluid thickens. Shear thickening. So here's the plan. If Judy and I make enough cornstarch mud, could we run across it? Let's find out.
Yeah, I think mine is just the right consistency. How's yours, Judy?
I think I'm ready too. This is much harder than I thought.
Yeah, it's really hard to get it mixed at the very beginning, but mine is ready to go. Okay, here we go. First batch. You ready?
Yep.
Dump it in. Woo! Woo! I thought that would be more.
I thought so too.
It's really not filling this up very much, is it?
No.
Huh, that's a lot of cornstarch. This is
This is great, but I think we're gonna have to go a little faster than this.
I think we need some sort of mixing device.
Yeah, I mean, we don't have to do this by hand. We can get some sort of machine to help us.
Yeah.
Right on, high five.
Oh,
We shouldn't high five when we have this stuff on our hands.
Nope.
Yeah, good call. This science is delicious. This is rock candy. It's basically crystallized sugar, and you make it by turning a solid into a liquid and then back to a solid again. Here's how you can make it at home. You need a container that you're not gonna need for a while, and some water, some sugar, you can use brown or white, I like to use brown, and an adult. Here's why you need an adult. You wanna dissolve 3 cups of sugar into every cup of water, and you can't do that unless you heat the water. So get an adult, a saucepan, and heat the water up, pour the sugar in, and keep stirring until it's all dissolved. Then pour it in your container and let it cool down. Then you'll need a shish kebab skewer, which is something you can get at the grocery store. Cut it down to the right size so it fits nicely into your container. And then dunk it in your sugar and get some crystals coated around the stick. These are seed crystals and they get the whole process started. And now you have to wait for these to dry, otherwise they'll just fall off the stick when you put it in the water. So I've got one here that has dried out. You'll also want something to keep it from falling in the top of the container, so I'm gonna use a clothespin. Put it in there and dunk it in the container like that. And now for the final step, if you want, you can add food coloring. I like to use red because it reminds me of science. And I'm gonna use the stick to actually stir that up a little bit. There we go. Now, the dissolved sugar crystals in the water will slowly grow on the crystals that are already attached to the stick, and it will eventually grow into a rock candy pop. But it takes about a week. No, I'm just kidding. I've already got one that's standing by. Here we go. This one has been growing for about 7 days. And there you go, rock candy. Delicious science. Now, how could we make this any better? I mean, it's crystallized sugar. It doesn't get any more maxed out than that, does it? Yeah, it does. Come on. This is a giant container of sugar water, and I've been brewing a massive rock candy crystal in it for a while, but it's sort of getting a little bit too big to fit out the top of the container, so you know what? I'm just gonna put that back in there and chalk that one up to science because, well, eating a rock candy crystal that big will definitely not be good for my teeth, so yeah.
So our big experiment is to take a whole lot of cornstarch and fill a trough to see if we can run on it. But mixing it by hand was going to take forever. So Judy and I got a drill with a mixing attachment on the end.
Whoa, sorry. All right, so Judy, I'm noticing a bit of a problem here.
what is it?
Well, if I mix at the top, everything's fine, but as soon as I get it a little bit deeper, and then it gets really tough, and the whole bucket starts to spin, and the drill stops.
Yeah, I think it's because the drill's trying to mix it too fast. When we're mixing it by hand, it's slow and you can still let it stay a liquid, but now you're just making it a solid.
Right, because it's a shear thickening fluid, so if
Exactly.
you hit it really quickly with something, like the blades of this spinning really quickly in the thing, it'll suddenly turn into a solid, and it'll be really hard to mix.
Yep.
So we go slow. Going slow. Going slow. Suddenly realizing that if we go slow, we'll be here forever.
Yep.
You know what I think we need? Whoa, sorry. You know what I think we need? We need a different way to mix this.
Yep.
We need a way to mix more of it, and we need a way that it doesn't hit it with blades that suddenly go through it really quickly.
Something that can mix on a large scale, but slowly.
I have just the thing. Come with me.
All right.
The interesting thing about bubbles is they're a gas surrounded by a liquid. So get some dish soap and some water, and then be science maximites and find things around the house that you can make bubbles out of. Just about anything that has holes will do. Or,
Or I like this one. I call it the loud bubble. Or now it's time to max it out. I'm here at the Ontario Science Centre, and this is Anthony. Hey, Anthony.
Hey, how's it going?
Good. So you are amazing at bubbles.
I am. I've been practicing for a while. Let's get started.
Okay.
You're gonna make an okie dokie sign like this.
Uh-huh.
You're gonna dip it right into our bubble solution. Come on, get right in
Okay,
there,
right
right in
in.
there. Make sure you get it all. Oh, that's a little too much.
Well,
That's
then I
good.
can make two.
And then you're gonna keep that okie dokie sign. You're gonna blow very gently.
Nice.
I brought these two giant sticks here, and I don't know if you noticed, but I've got a smoke machine here.
Right.
So we'll turn that on, and then if you press that green button there, you're gonna shoot some smoke, and we're gonna try to catch that smoke in a giant bubble. You ready? Okay, and I'm gonna try to... Oh, that was so close.
great.
Did you see that one? You give it a shot. Nice! Oh, check that out! That was amazing! That was huge. Try it again. Let's see if I can get the smoke machine. Here we go. Go for it, go for it. Push right towards. Oh, check that out! You did it! Look at that! Look at that! No! Smoke, and it bounces on the floor because the floor, it doesn't have any oils like our hands do. Isn't that amazing?
That was
oh my
great.
God, that was so cool.
That was great. You know what I think we should do?
What's that?
Giant bubble, tons of smoke.
Done.
Okay, here we go.
Let's do it. You ready?
Giant bubble, tons of smoke. Go.
Awesome! Oh my God! Look at that! Amazing! Look at that! That's crazy!
Max out bubble. Well, there you go. Giant smoke-filled bubbles.
Awesome!
Yeah.
Judy and I tried mixing the cornstarch mud using a drill with a mixer attachment, but it didn't work. We should have known better. Here's the mixer in our cornstarch mud. Usually, a mixer works by going really fast and mixing everything together. But remember that cornstarch mud is a shear thickening fluid. So, when the blades of the mixer tried to go fast through the cornstarch mud, it did what it always does, turn solid. The faster and harder you try to move it, the more solid it will become. This means the only way to mix it would be if we made the drill go very, very slow, which wouldn't speed things up at all. So with the drill another lost cause, Judy and I need the biggest thing around that could mix stuff
Come
up.
on back. Good. Little bit more. Perfect. A cement truck is the perfect thing to mix because all we have to do is get all the cornstarch up in here and it'll mix it and it doesn't move it too fast. It goes nice and slow, so hopefully a shear thickening fluid will be fine. I'm gonna get Judy. She's driving the truck. Hey, Judy, that's perfect.
The only problem is we needed to get all of those bags of cornstarch into the hopper of the cement truck.
I didn't think it'd be this messy.
We needed to call the entire Science Max build team to help us out.
This is possibly the messiest thing I've ever done. Awesome! Woo! Hey, Judy, you wanna lift up any bags?
I'm okay, thanks.
That's okay. I'm having a lot of fun, so I can do them.
Cool.
Oh no! Oh no! Oh no! Yeah! I got most of it. I got most of it. All right, I think we're done. I think that's enough bags. Let's start the mixing! So, what do you think, Judy? Do you think it's gonna work?
I think so, because you're mixing at a very large volume, but at a very low speed.
Yep.
So throughout the process, it'll stay a liquid until we're ready to run across it.
That sounds exactly like the kind of science I like to see. You know what I really like is that every time I move, more cornstarch comes off. It's like I'm a human fog machine.
This is liquid nitrogen. Nitrogen makes up most of the air we breathe, but if you get it really, really cold, it turns into a liquid. The fun thing is you can use it to make other things really, really cold too, like this banana. I have frozen this banana solid thanks to the liquid nitrogen, and normally a mushy banana would not be able to hammer in a nail, but, whoa, because it's frozen, I can hammer this nail into this block of wood. So that got me wondering, if I can turn a banana into a hammer using liquid nitrogen, could I turn a pumpkin into a sledgehammer? Let's find out. Pumpkin sledgehammer, take one. No, I think the answer is no. You cannot turn a pumpkin into a sledgehammer with liquid nitrogen. All you can do is make a really, really big mess. I'm gonna have to clean this up, aren't I?
Now we have a cement truck to help us do the mixing for our cornstarch mud. After making a giant mess getting the cornstarch into the cement truck, it's time to see if it worked.
Hey, Phil, how's it going?
Yeah, it looks like it's mixing pretty well. I'm really glad we're not doing this by hand, because it'd take a really long time. We've almost got it at the right consistency, but it's taken some time. But it's getting a little dark out, Judy. I don't know, do you want to quit and go home?
No.
Of course not. That's not what we do in science. Oh, here we go. Yeah!
Awesome.
All right, let's see it. Let's see if it's... I like how it comes down in little steps. And look, it's working just like it should. I hit it, and it's solid, but you can see it's pouring like a liquid. Yeah, here comes a big wave.
Wow.
Here it comes. Oh! Wow!
And it's totally filling up.
Oh yeah, filling up really fast. I think we should stop pouring very soon.
Yep, we may not have a big enough trough. Yep,
Liking it.
it's good.
Yeah. I think it's time. It's not even done pouring, but I'm gonna try it. Okay, you ready? Whoa.
Oh, and you did it!
Whoa. You can't. You have to get back onto the sides before you stop moving.
Or else it becomes a liquid.
All right, it's your turn.
Okay.
Here.
Go.
Okay, ready?
Okay.
You gotta hit your feet really fast.
All right.
Here, go. Yeah!
This actually works.
Because cornstarch mud is a shear thickening fluid, it means it stays a liquid until you hit it suddenly, like with your hands, or in this case, our feet. And then it turns to a solid. So as long as Judy and I keep slapping our feet down with enough force, we can walk on top of it.
One more dance.
All right.
And
let's
tell you
do
what,
it.
we'll do one more dance.
All right, let's do that.
Okay, ready?
All right.
And go. All right.
All right.
There you go.
We've done it.
Solids, liquid, gases. Thanks very much for joining us on Science Max Experiments at Large. Woo!